Michael Borsche, the Managing Director of Amiga Engineering. We started in 1988 and we were primarily a traditional machine shop doing work for the heavy transport industry, and that developed into doing work for the oil and gas industry. And along with that we got into CNC machining and eventually built ourselves up to owning our own factory and growing. We then said, well, what's next? So we got into 5-axis machining, and on top of that we sort of said, well, what's next? And then evolved into doing 3D metal printing and now polymer printing, and now we're into reverse engineering and scanning. Well, it's interesting. 3D printing has changed our business in a lot of ways. We were hoping it would attract a new level of clientele, and this has brought in designers and engineers more focused on what we're doing. But along with that, of course, comes a new level of quality, because you've then got to measure these complex parts. But the 3D printing in metal was certainly a great add-on to the business, and being basically the premier service bureau in Australia for metal printing, it's brought a bit of light on the business and helped us grow. Now, 3D printing being a complex technology, it's certainly made us think more about all the processes involved, and that's highlighted the ability to measure some of these complex parts. Originally, some of the earlier 3D printed parts were quite simple, but as designers were able to open up and free their minds to complex parts, multifunctional parts, so more parts in one that can do various things. It seemed to me that we needed to find new ways of measuring these parts. Lots of curves, faces and underlying ledges and very intricate detail. Suddenly the standard measuring instruments weren't really enough. Micrometers and verniers didn't cut it. Our CMM, even which we've had for a number of years, we struggled to measure some of these complex parts, and in fact we would spend a long time programming, and we needed fairly skilled operators to run the CMM to measure some of these parts. Now, really the programming time, which is just too long, it takes a long time to get it all operational. You could do anything anywhere from hours to half a day, even for days. We had a turbine blade recently, which we were trying to measure, and it got very, very out of hand. A lot of detail and underhanging ledges. This certainly highlighted the fact that we needed to find a better solution. Well, really, I've watched the evolution of scanners over the years, and I've found them to be a little bit wanting. There's arm scanners, there's probes and digitisation of those, and the add-ons of laser scanners and that sort of thing, and that's been quite good. But really, to do something at a level of getting enough feedback and data for machining purposes at high level, high tolerances, it hasn't been there. But now we've come across the ATOS Q, which has only just been released worldwide, and we're the first ones in Australia to actually get one. We've found that this is just amazing. It's down to 6 microns we can measure to, so that's really highlighted to me. This is the time to get into this, and we can use it for everything we do within the business. Well, really, this is being a world first and being first in Australia was one reason to get the ATOS Q, but we were looking really for its level of accuracy, and this to me wasn't really available until the ATOS Q came out. And the ease of use, I've looked at CMMs and the complexity of how they are to the training you need to go to get to an advanced level to be able to use them well. And with this ATOS Q, it's really simple. Within a few minutes, you've got a part measured, and the level of detail you get is just second to none. You possibly get it from the CMM. Just started developing a small jet turbine engine, and as part of that, we 3D printed this part here, and scanning of the aerofoil shapes within this part certainly helped us get to the end result we needed. Previously, trying to use a CMM to try and measure in these little blades and the curved sections and the aerofoil design of the whole part was virtually impossible. Certainly on something this small as well. Even if you 3D machined this, like on a 5-axis machine, you wouldn't get the level of detail you've got in the corners and the fine edges on here. Not impossible, but very hard to do. Whereas obviously 3D printing and machining, and then the ability to scan this and then hand it to the machine operator with data that helps him align it in the machine to find the best setup, because we're after balance on this part. We want it to spin at high revolutions, something like 48,000 RPM, and it's got to be very balanced. So understanding where your 3D printed part is, comparing it to the model and giving that feedback to the CNC machinist is paramount. Yeah, well, the traditional machine parts, some of the parts we do in our factory are quite large. We've got a 4.3 metre travelling column milling machine, and if we've got to measure where our machining is in comparison to other parts of the machining on, say, a large pump base or something like that, it's difficult to figure out. You can use the machine's built-in accuracy to probe it and get measurements off. But if you've got to turn parts several times, you need to really take a measuring tool to the machine. So the scanning offers that ability to do that. We can take the scanner and we can scan the whole part, and we can see things that we could never see before. It's not just a matter of where a hole is or where an edge is or how flat a surface is. You can get complete comparisons to 3D models as what you've machined. It's outstanding. Well, it's a fairly lengthy process. You need to have obviously a starting part, and if there's something that's become obsolete or broken, or this part that there's no longer drawings for, that you can create CAD models. Scanning is one way of scanning the part and giving you back a base model to then work from. And as an example, we had a headstock off a fully carbon fibre bike, a racing bike of the highest level. And the guy wanted to get something a bit stronger, and we wanted a 3D printed titanium part. So we went through the steps and processes to go from that carbon fibre component, which he didn't have drawings for, didn't have any CAD models for. It was handmade, and we were able to produce a CAD model out of that, produce a printed part, and of course that can then go into production.